we're doing the multiple choice gravitation packet, and we're just going to go in order. So number 1 says the mass of planet X is 1/10 that of Earth, and its diameter, so the mass is 1/10, number 1, the mass is 1/10, and the diameter is 1/2, okay, of Earth. The acceleration due to gravity. So they're so when you're reading the question, you're going to say, what are they asking for? They're asking for the acceleration due to gravity, which is little g. So little g is equal to big G, the universal Newtonian gravitational constant, the mass over r squared. But now they told us that the mass is 1/10, so it's m over 10, and they told us the diameter is half. Well, you have to remember that diameter is r over 2. Well, r is actually the distance, so this would be r over 2 squared. And now you have to just do the all the algebra stuff. Because remember, this r is the distance from the center of mass to center of mass. So if I do the math, all right, so now you just have to do like fractions. So I would square, so you would have gm over 10 is r squared over 4. And remember, like we just said, if the diameter is half, the radius is half, so you don't have to half it again. So now what I would do is I might just stretch out how I do fractions, and I would do like gm over 10 is 4 over r squared, okay? So then if you reduce the fractions, this is 2/5. So it'd be gm to 5r squared, which is, yeah. So, because we know what Earth is 9.8.
Mass is 5.98 times 10 to the 20.
Well, no, you just have to put in, okay, so the way to do this is, it's basically 2/5 that of Earth. So you just say 2/5 of 10, and that's how you do it. So 20 over 5 is 4, and that's how you get 4, because on all the multiple choice questions, you're going to use little g as 10. So does everyone understand why I just did this? Because the rest of it, the g, the m, and the r squared, is the way it looks in the original equation. So what do you need to know to do this problem? The only physics you need to know is you need to know this equation. And this is like a typical type of question that they ask you, what if you change this and that? How is it different? Does that make sense? So they're just saying, do you know this equation? But they're making it a little harder because with all the little, you can make a mistake, with either squaring this. You can make a mistake with, a lot of times if you do this in your head, you might make a mistake. That's why sometimes they just scratch it out real fast, with the numbers. But everyone's different. So number 1 is B. All right, number 2. This is typical AP questions, but what they do now is instead of 2 columns, they have 3. The key to doing this is you don't read from left to right in English, you read from right to left, because normally the column all the way to the right, you can cross off, eliminate more choices. So that's like a trick to doing these, and there's going to be a couple of these on the test. All right, so it says a satellite travels around the sun in an elliptical orbit, as shown. So we know that the sun is not in the center because this is an ellipse and it has 2 foci. So we know, so one of the things that we talked about was the best way to think about this is also, I always think about stuff, especially when you get to speed, as far as conservation of energy. That's the best way to think about it. So you're not thinking about the speed, you're thinking about the energy. So it says, so it's going from X to Y. So here's X. Whoops. So at X, it's farther. So when it's farther, that means it's going to have more potential energy and it's going to have less kinetic energy. over here at y, the kinetic energy is going to be a max and the potential energy is going to be a min. Well, where the potential energy is a max, this is where you're going to have V max, and where the kinetic energy is a minimum, that's where you're going to have V min. So which of the following is true? So a satellite travels, it's going from X to Y. So it's starting here and it's going here. So make sure you don't read it like backwards, because they're always going to have the choices if you like did the reverse. So let's go all the way to the right. So on the right, it has to do with the angular momentum. Well, Kepler's second law is based on conservation of angular momentum. So we know the angular momentum is constant. So that's one thing here is angular momentum is constant in both an elliptical and circular orbit. All right? So now, because we know that this is constant, do you see on the right? And this is a typo, so I'm going to eliminate these two choices. Now, what's happening to the speed? Well, again, this is where you're going to think about conservation of energy, because it's going from here to here. So here, you're going to have less kinetic energy, and here, where you have Kmax, you're going to have Vmax, so the speed is going to increase. So the speed's going to increase. So the only other one that has increases that was constant is this one. So the choice is D. All right, number 3. It says a newly discovered planet Cosmo has a mass 4 times that of Earth. So again, this is 4m. The radius of Earth is RE. The gravitational field strength of Cosmo is equal to that of the surface of Earth. So they're asking you questions. So this is just like number 1. This is, do you know this equation? G is equal to gm over r squared. So they want to know r. So I'm going to rearrange this equation. The only difference is I'm going to put in 4m. So I have r squared g is equal to gm. And, you know, on a multiple choice, you're not doing intermediate algebra steps like I'm showing you right now. And then, you know, you can easily rearrange it. I would not do something like this in my head, though. So then r is equal to gm over little g square root. But now they want to know it's 4 times. So it's g 4m over little g. So now here's my original equation. Here now is what r is equal to, so the difference is between this and this is 4 underneath the radical. So radical 4 is equal to 2. So the answer is 2, which is letter C. So again, this one is exactly like number 1 as far as this is the equation, then you're asking you something that's a little bit different. All right, number 4. 2 artificial satellites, 1 and 2, orbit the Earth in a circular orbit. So we have their picture right here. As shown, if R2 is twice of R1, the acceleration of A2 and A1 of the 2 satellites are related by what? So the acceleration is, again, little g, which is going to be gm over r squared. Okay? So basically what I'm doing is I know this, and I know that R2 is equal to 2R1. So what I'm going to do is I'm going to take this equation, and I'm going to have gm r over 2 squared. Oh, thank you. And so this would be gm r fourth over 4. So now I'm going to look at that and say, so the difference, the g and the m is the same. So the difference between this and this, if this is down here, the difference is,
Should that be r squared over 4?
yeah. So the difference is going to be a 4th. So that's going to be choice E. All right, number 5. So obviously these are from like different years. Obviously this is an equation that they like to test on the multiple choice. You see what I'm saying? So number 5, it says the radius of Earth is approximately 6,000 kilometers. Now again, all these questions were written when you didn't use a calculator. The acceleration of an astronaut in a perfectly circular orbit is 3,000 kilometers. If the acceleration of so they want to know what the acceleration is. So again, G is equal to gm over r squared. So you have to look at the difference of, first of all, what the difference is from G to G. So I just looked at a ratio. So if he was 3,000 kilometers, because the mass of the Earth is the same and everything else, and then here it was 6,000, and then what's 3 divided by 60? Let's say about 1/20th. And then you do 9.8 minus 9.8 over 20, and then you get some answer. Well, if it's 9.8, and then this is going to be a teeny number, right? So it's going to be less than 1. So if you look at the choices, 0.055, 9, and 11, it has to be 9, because it's going to be a little bit less than 9.8. I mean, luckily now you get to use a calculator. And that's kind of a weird question anyway. All right, number 6, it says a satellite moves in a circular orbit. So the key thing is when you're reading these questions, is it circular or is it elliptical? Because in a circular orbit, the speed is constant, and in a circular orbit, we know that the centripetal force is equal to the gravitational force. So 6, a satellite moves in a circular orbit with a speed v0 at a distance r from the center. For this satellite to move in a stable circular orbit at 2r, again, they're just asking you, like, do you know your equations? So you know that the centripetal force is equal to the gravitational force. So like mv squared over r is equal to gmm over r squared. But you don't have to derive this equation. If you remember on your equation sheet, so you can go ahead and do all this and like cancel stuff out, but when you do the algebra, this comes out to be v is equal to gm over r. So again, this is an equation that they ask often. This is the speed of something going in a circular orbit, so I would just make sure you know that, because you don't want to waste time deriving the equation. And there's a lot of equations for different things for orbits, like escape speed and stuff like that. So these are things that are important to put in your calculator. So now we just look at it, so it's radical gm over r. So now they say, well, what if it's 2r? So if you have gm and then you put 2r, the difference is in the denominator 1 over 2. So that would be choice B. See how the radical 2 is in the denominator? Does everyone see that? Because see how the 2 is in the denominator here, but it's under a radical. Okay. So most of these equations, you notice a lot of these are just like, do you know the formulas? You know what I mean? And then they're just like changing stuff around. All right. All right. So, a newly discovered planet has twice the mass of Earth, so it's 2me. We don't know what the planet is. But the acceleration due to gravity is exactly the same as Earth's gravity, the radius of the new planet. So now what's the planet? So the gravities are the same. So again, this is the same equation. G is equal to gm over r squared. So they obviously like this. Now, what did they say is the same? The little g. So what you do is you set one equation equal to the other. So you have the GME over RE squared. This is the Earth. And then for the planet, the mass is twice of Earth. And then I don't know what the radius of the planet is. So now I'm going to start like getting rid of stuff. So obviously, what can I get rid of? I can get rid of the G's. Does everyone see what I'm talking about? You can actually get rid of the mass of the Earth, right? So now this is just going to be in terms of the radius of the Earth. So 1 over RE squared is equal to 2 over RP squared. I guess I'll cross multiply. RP squared is equal to 2 RE squared, so the radius of the planet is equal to radical 2, and then if I square root that, RE, which is choice C. Do you see how all these really are like an exercise in algebra? So once you know the equation, and they use this same equation over and over again from different years. All right, number 8. A small mass is released from rest at a great distance from a large stationary mass. Which of the following graph represents the best gravitational potential energy U of the system of the two masses as a function of time? So I would first look at the equation. So U is equal to bless you. Yeah, minus G M1 M2 over R. So the answer is D. Because this is, here's the thing about the graph. The graph is the potential energy as a function of time. Okay? So it's a function of time, not a function of R. Does everyone understand what I'm saying? And I know on other tests, they've had the same similar type of a question, but it was as a function of R. So if it was a function of R, wouldn't it look different? If it was a function of R, it would be linear. But this says as a function of time. So how do you know how to do this? Well, you have to know the relationship between U and F, because the slope of you have to think about the relationship between potential energy and force. Okay? So this question is trickier than it seems, because most people are going to think about this equation and they're going to pick choice B instead of the correct answer is D, because they're going to think it's a U versus R graph. Because they've typically had a U versus R graph on here. Okay, so this one, I would say this one's kind of a tricky question, only because everyone's said, oh, here's potential energy, here's the equation. What happens, as R increases, but it's not U versus R, it's U versus T. So you have to know the relationship between potential energy and force. So the answer is D. So. I just wrote down the equation because that was the first thing that I thought of, but you have to look at the relationship between U and F. Okay? So,
what is that relationship?
So, and then know the slope of the graph is proportional to the force.
Is the what for the force?
It's proportional because
So
it's
the
increase.
U is F.
Right. So you're going to see how it's. Sorry. Yeah. So I think this is a tricky question because most people are going to say, oh, it's a U versus R graph, and they're going to put choice B. You know what I mean? Because that's like a typical question. All right, number 9. So it's the first thing I'm going to do is look. It's elliptical. Satellite closest and farthest. If the satellite speed is v1 at the closest, what's the speed the farthest? This, now you're looking at the choices, okay? We know in an elliptical orbit that angular momentum is conserved, and we know that energy is not. So, it's the same satellite.
MVR.
Yeah, we're going to do conservation of angular momentum. So MVR is equal to MVR. So we're going to, I guess, call things 1. Do they do it 1 and 2?
Yes.
Okay, so 1 and 2, and wait a second. I think I'm doing.
The other one should be R2.
Okay, so we're solving for?
V2.
So V1 R1 over R2 is equal to V2.
Yeah, that's it.
Oh, that's choice A. All right. All right. Number 10. Refer to a ball that's tossed up from the surface of a small spherical asteroid with no atmosphere. The ball rises to a height equal to the asteroid's radius. So, again, they're saying this is like this, and then it goes up here. And then it falls straight down towards the center. What forces, if any, act on the ball on its way up? So this is more like a conceptual question. So the only thing acting on it is gravity, so that's A. Oh. All right, should we stop?
Yeah.
Okay.